final presentation of today, and indeed our final presentation of the week. Thomas Braun from TU Berlin and Alexander Schwandt from FKS Maschinenbau are going to be talking about lightweight construction strategies again for rail vehicles. So they'll be talking about AI-monitored robotics for additive processes like fused granular fabrication even, arc spraying, cold spray, and producing topology-optimized stiffened train segments. So, gents, over to you.
Thank you.
Thank you.
So, welcome to our presentation. I am very pleased to present to you some results of our common research project regarding additively manufactured lightweight structures for train applications. My name is Thomas Braun. I'm a research scientist at the Institute of Machine Tools and Factory Management, and to my right-hand side is Alexander Schwandt from FKS Maschinenbau GmbH. First, I would like to introduce just briefly our institute, the Institute of Machine Tools and Factory Management of TU Berlin, and we are researching in projects in regard of additively manufactured parts and additive process change in general regarding industrial applications and metal parts mainly. Related to the pre-processing, process optimization, up to the whole post-processing and the quality assurance. So I would like to hand over to the introduction of
Thank you very much for the short introduction. My name is Alexander Schwandt. I'm the tech lead in the programming department of FKS Maschinenbau GmbH in Berlin. The company was founded in 1992. It's a mid-sized enterprise employing 25 colleagues. And our key portfolio areas are in the turnkey solutions, where robot-based laser welding plants are provided, also assembly plants, press plants, all the needed peripheral systems, which are also included in these systems. Spray technologies, and of course the robot-based additively manufacturing technologies, the automations like the cold spray cell, what we are now explaining and presenting. So now I would hand over back to Thomas.
Right. So one brief look on the agenda, what we are about to talk. So I would like to present the use case and the aim of the research project. Would like to focus a little bit more on the cold spray technology that's being used, and then the system layout, the system architecture, which will be presented by my colleague. So the aim is to reduce the weight of parts of trains. So we are talking about train compartments, train wagon segments, which we aim for a weight reduction of at least 10% using topology optimization of conventionally built parts, which are usually applied by welding structures. And what we did is to use the very same part as a starting point, do a FEM analysis, a topology optimization, and having a result which give us a result of a much lighter part in general. And this then we adapted to our robot-based additive manufacturing processes to make it in line with the used technologies and with the robot-based technologies, basically, which are used to build those very big, large-scale parts that we aim for in general. So how did we do it? We used a process combination of 3 different types of additive manufacturing processes, which are all robot-based, because we try to combine them in one process chain to build those large-scale parts using a fabricated or fused granular fabrication process to build up the thermoplastic, so the 3D geometry of a hollow structure to give us the lightweight shape of the geometry that we aim for, and then coat this plastic part with a aluminum coat or coating that will present a substrate for us made of aluminum so that we have the shape but resistant enough and mechanical strength, having a mechanical strength sufficiently to then apply the cold spray process with the steel coating, the steel deposition, which is the load-bearing part of the whole geometry. So this is then the cold spray part of the process chain, and then we will dissolve the plastic shape-giving part of the whole construction, and that will leave us with the result of a lightweight structure resulting in a weight reduction of at least 10%. So I would like to focus here a little bit more on the cold spray part of the process chain. How does this process work and what are the principles? We see this cold spray gun, which is the tool in this process and the main part, which is basically a pressurized cylinder which is thrown through by a carrier gas, a process gas. In our case, it's nitrogen, which is loaded up with thermal energy up to 1,100 degrees Celsius and pressurized with up to 60 bars of pressure. And then we have a Laval nozzle, which applies the very same principle that is being applied also in any kind of jet engine, basically. So this Laval nozzle accelerates the jet stream up to 1,200 meters per second, so basically Mach 3. And those carrier gases then apply and accelerate the powder particles. In our case, it's steel 316L, also to supersonic velocities, loading those particles up with very high kinetic energies. And those kinetic energies then will form a massive deposition on the substrate, in our case, this 3D hollow structure of the trains, to deform a massive deposition with very high density and very low oxygen content. So this is the basic principle of cold spray. And now I would like to hand over to my partner, who will show you how the process control was being designed.
Thank you so much. Yes, the proposed additively manufacturing automation is based on an industrial robot, the KUKA KR120, which is mounted on additional 7th linear axis for the increased reachability. The robot is guiding a cold spray gun, fitted also with a laser profile scanner from Keyence. And the entire automation is situated in a cell with a venting and filtering system accordingly to the requirements for a cold spray application. On the right we see a simulation. Hopefully, it's not playing.
No.
Maybe you could, okay. So we have a rough understanding how a simultaneous application of the cold spray process with a scanning process could look like while being applied to that part. And in the result, we need that scanner to get an idea how the result looks like, what we have produced on that surface. The general system architecture would look like this, that we have central PLC Siemens controls, which is combining together the cold spray peripherals, the robot controls, the CAR-C5 in this situation, the laser profile scanner with a Profinet network. Additionally, there's also a processing unit introduced, which is providing the following functionalities. It's first of all a data logger, which is recording all the process data from the internal robot information, positions, torques, and so on. The settings of the technological systems, like the cold spray, and also the feedback signals and results from the profile scanner. Later on, this data is processed, referenced, and also stored in a specific data structure into the database. Based on the database then, later on, any adaptations to the process will be calculated. And then any adaptations of the process can be also then implemented. Now, an essential role in this entire adaptation process plays the profile scanner. There are several capabilities. So when we consider this flat test sample, for example, it was scanned with a profile scanner, and we have a topological representation of that profile, but it's not referenced yet. And there's the question, how can we detect any defects on a free-shaped surface? And for that one, generated reference surfaces can be used as a reference, which are aligning to the geometry of the produced part. The generated reference surfaces are specified by certain extraction step parameters, which is actually more or less a pixel parameter in the pixel space of the sensor's images. And then we see the difference, what defects actually can be detected in the flat area of that test sample. But also other tools are available, so any profile measurements on that test sample can be also done, and these numerical results can be then forwarded also into the logging device, which then later on can be also used for any further adjustments or training of AI algorithms, for example. In the following, I would like to present how we were running first practical function tests in the automated cell by attaching the Keyence profile scanner to the cold spray gun, where a test sample was in 3D scanned and intentionally introduced defects were detected. On the right, we have the result of this entire logging process. The robot was executing a CNC program, which was then in real time logged, and we see the result where in blue crosses the defects were located in relation to the part, in relation to the movement of the robot. So how now, based on that knowledge of that data, we could implement any adaptation algorithm? So here's a very easy use case where we were just proposing an approach of a black box, like consisting of an AI-based algorithm or maybe a hard programmed algorithm. At the input, we have the 3D distance between the current TCP position of the robot to the coming next located defect we are going to pass by. And in relation to all this information, we then get at the output any correction, for example, of the trajectory speed of the robot. And this is done in each and every iteration when the robot is actually executing the CNC program in this case. But furthermore, we have also capabilities of adjusting, for example, the tool configuration. So not only the robot trajectory speed is a variable, but also the orientation, or maybe a linear distancing offset could be also useful. So all these additional adaptive functionalities are introduced in that system, and the trials are ongoing. So going more in detail to the first presented opportunity of adjusting the robot's trajectory speed, we have here the results. There was a correction law function used, which is presented, and this function is providing a very smooth, jerk-free introduction of any changes to the robot speed. And what we have here is actually a record of the generalized robot speed, that's the over O4 Pro, for example, which was changing the speed. So it was changed firstly in the area of the first defect, it was decreased, but then it was at the second defect, which was categorized a bit differently, it was increased. So that's a very simple and good to understand example how such a adjustment could look like. But furthermore, that's a hard-coded algorithm. Also some AI, artificial intelligence algorithms could be used. So based on the sensor images, also some defect area segmentations could be done with based on AI. And referencing the robust trajectory in the image pixel space coordinate system would also allow to get this feedback channel to the robot in what areas which changes need to be done. So this approach is just the first glimpse how it could be continued later on, but at that stage we come actually to an end of the presentation. Thank you for your attention.
Thank you.
Yeah.
So if there are any questions, we are very happy to answer them.
So what are the next steps in this project then for you?
The next steps are to combine all the technological parameters where maybe in the first impression we don't see any big interaction between them. So here we see big potentials, maybe also to work more with artificial intelligence algorithms.
Mm-hmm.
Yeah.
And in terms of application areas, where do you think this could go?
That could go much more further. So now we have it in the rail industry, actually. But yeah, so there are also applications in the air, in the aerospace.
Absolutely,
area.
that's a very good question, because with cold spray and with those other robot-based additive manufacturing processes, we are generally looking to manufacture quite big parts, and the quality control in situ, like having a feedback loop, and to make sure we don't have any defects in the manufactured part is quite essential. So we use this laser scanner system and the AI recognition of any kinds of defects that can occur to make sure that those parts are ready to use in the first place.
Okay, perfect. If anybody has any question that they want to ask publicly, I can bring you the microphone. If not, that is the end of this session, so you can come and ask your questions in private. Thank you very much to our speakers. Nobody wants to go last, but somebody has to, and you did, so much appreciated. Thank you very much for that.
Thank you very much.